All right, today we are tuning in to the invisible world of aviation radio. I mean, think about it. It's this unseen symphony of signals and commands that guides every single flight. And it's the critical system that keeps our skies, well, incredibly safe. It really does seem kind of magical, doesn't it? You've got a pilot at 30,000 feet talking to someone on the ground who might be hundreds of miles away. How in the world does that signal bridge that huge gap? Well, that's the exact question we're going to answer. Okay, so let's dive right in. To understand how any of this works, we first need to get our heads around one single fundamental rule of physics. This is the golden rule that governs pretty much everything in aviation radio. And this is it, the golden rule. The VHF, or very high-frequency radio waves that planes use, travel in a straight line, almost like a beam of light. So if there's something in the way, like a mountain or even just the curve of the Earth itself, the signal gets blocked. It's really as simple and as complicated as that. So wait a minute. If the Earth is curved and these signals only travel in a straight line, how does long-distance communication even work? Well, the answer is all about getting a better view. You know, this is such a classic scenario for anyone who's ever listened in with a scanner. You can hear one half of the conversation perfectly clear, the pilot, but the controller on the ground is just static. It feels weird, but it makes perfect sense once you remember that golden rule. And this slide shows us exactly why that happens. The plane, way up in the sky, has a clear, straight, unobstructed line of sight right to your radio antenna. But the control tower on the ground, from 50 miles away, it's actually hidden from you by the curvature of the Earth. Its signal gets blocked before it can ever reach you. This really drives home the most crucial point. In aviation radio, altitude is everything. And you can see just how directly that relationship plays out in the real world. At only 1,000 feet up, a plane can talk for about 40 nautical miles, but you get that plane up to 30,000 feet and that range explodes to over 200 miles. The entire air traffic control system is built around this simple, predictable piece of physics. So, knowing these physical limitations, the world of aviation built this incredible human system to manage it all. It's not just one person talking to one plane. It's a highly coordinated performance. You really have to think of it like a symphony orchestra. Each controller is a different section, the strings, the brass, the percussion, and each one has a very specific part to play at a very specific time to create a completely seamless and safe journey for that aircraft. But before the symphony can even begin, the pilots need their program notes, and that's where ATIS comes in. It's just a looping broadcast that gives them all the basic info they need for the day. Wind speed, which runways are active, the barometric pressure. This way, everybody is on the same page before they even make their first call. Okay, so now let's actually see how this whole symphony comes together. We're going to follow a single plane's radio journey as it departs. This is where we'll see this precise series of handoffs from one controller to the next. As a plane gets ready for takeoff, it follows this exact four-step handoff. The pilot is going to talk to 4 different controllers, one right after the other, and each one manages a very specific piece of the departure puzzle, getting the plane from the gate all the way up into the sky. So the very first conversation happens while the plane is still parked at the gate, not even moving. The pilot calls up clearance delivery to get their flight plan officially approved. It's kind of the bureaucratic part, but it is an absolutely essential first step. And it sounds just like this. You hear the controller confirm the destination, the specific departure route, the runway, and then they assign a unique 4-digit squawk code. That code makes the plane's transponder identifiable on every single controller's radar screen from this point on. All right, once that clearance is confirmed, the pilot switches frequency and talks to ground control. This controller is basically the traffic cop of the entire airport surface. They manage every single vehicle moving on the taxiways, from jumbo jets to little baggage carts. Their one job is to get that plane safely from the gate to the edge of the runway. And here you can actually hear the controller giving specific taxiway instructions, taxi Sierra Bravo, and then telling the pilot which frequency to switch to next and exactly when to do it when they're holding short of the runway. And now for the main event, tower control. This person owns the most critical piece of real estate at any airport, the runway itself. They sequence all the arriving and departing planes and give that all-important final command, cleared for takeoff. The moment the wheels leave the ground, the plane gets handed off one last time. Departure control takes over. They're the ones watching on radar, guiding the plane as it climbs, and making sure it follows the correct path away from the airport so it doesn't conflict with any other traffic in the area. And this is what that first check-in sounds like. The pilot states their altitude and call sign, and then asks the controller to ident. That just makes their little blip on the radar screen light up for a second, so the controller can positively identify them. And just like that, the handoff is complete. So, this invisible world, this symphony, is happening all around us all the time. And the amazing part is, you can actually listen in yourself. It just takes knowing where to look to find the right frequencies. If you're curious, these resources are fantastic places to start. Skyvector.com has a huge worldwide database of airport frequencies. You can just type in your local airport and see the whole list. And for those of you in North America, you can even pull up the exact departure charts the pilots use on flightplan.com. It's a really fascinating look behind the curtain. Now, everything we've talked about so far is based on that line-of-sight VHF radio. But that only works when there's a ground station to see. So what about a flight over the middle of the Pacific Ocean? For that, pilots switched to something totally different: high frequency, or HF radio. As you can see here, unlike those VHF signals that just shoot straight out into space, HF signals can actually bounce off the Earth's ionosphere. This lets them travel over the horizon, which makes communication possible across thousands of miles of empty ocean. So we've seen this intricate symphony that manages planes near land, all of it built around the hard limits of line-of-sight radio. But this brings up a final, really fascinating question. What does that symphony sound like over the vast empty oceans, where the only connection is a crackling HF signal bounced from the very edge of space? Well, that's a story for another time.